Next, we're going to learn about visible light. Visible light is represented by the colors of the spectrum which make up visible light: red, orange, yellow, green, blue, indigo, and violet. These are easily remembered by our friend Roy G. Biv, and that'll help you remember the colors of the spectrum. You also want to remember that one end of the spectrum is ultraviolet light and the other end is infrared light. And this end of the spectrum represents more energy versus this end of the spectrum represents less energy. The energy is a product of the wavelength, which is also the color. So as you remember, wavelength is from peak to peak. That is the length of the wave, and light moves in waves. So as it moves down through the spectrum, the wavelengths get smaller and smaller and smaller, having more energy. Again, more energy in the color. You can also remember that by a fire. A flame in a fire, the blue tip flames will be the hottest, then the yellow, then the orange, then the red.
Alright, let's talk index of refraction, or simply a ratio that enables the comparison of the density of various materials. This is going to be found by dividing the speed of light through air by the speed of light through the material in question. An ABO question that often pops up is, what is the speed of light? And that's going to be 186,000 miles per second. Now, it's also important to remember that light slows as it passes through any medium. The higher the index, the more the slowing. Higher index materials, especially in plastic, are thinner materials. There's going to be 4 of these that you're going to want to memorize: CR39, crown glass, polycarbonate, and high index. Similar to how index of refraction is a measurement of the density of material, ABO value is a measurement of the optical clarity of a lens material. This is measured by the degree of dispersion induced by the lens material as the wearer looks away from the optical center of the lens. Color distortion is often the result of excess dispersion, and it's important to remember the higher the ABO value, the less chromatic aberration that you have. And also, the lower the ABO value, the more it breaks up the light into the visible spectrum and you start to see distortion. Remember that 60 is perfect. And also be very aware of a few of these for the exam. The ABO value of crown glass is 59, CR39 is 58, high index plastic is 36, and polycarbonate is 30. CCHP.
Now, let's learn some characteristics of plus and minus lenses. Plus lenses will magnify images. They are 2 prisms base to base, as illustrated here. They are thicker at the center, also as illustrated here. They converge light rays, so as light rays go through this, they again bend towards the base, so the light rays will converge, and they offer against motion. What that means is when you hold a plus lens up in front of you and you move it to the left, the image in the lens will move to the right, against motion. Minus lenses minify. They make an image smaller when you look at it. They are prisms apex to apex. They are thicker at the edges than at the center, and they will diverge light rays, meaning that, again, the light rays bend towards the base, so they're going to diverge light rays. And they will have with motion, meaning when you hold a minus lens out and you look at an image through it and you move the image to the left, the image in the lens will move to the left. Now, let's learn what against motion means with this +5 lens. When we place the lens over a straight line, you'll notice that when I pull the lens to the right, the image in the lens moves to the left. When I move it to the left, the image in the lens moves to the right. This is against motion. It moves the opposite of the way that I move the lens in the lens. Now, let's look at a minus lens, which will have with motion. So when we place the minus lens in front of the image, you'll notice that when I move it to the left, the image in the lens moves to the left. And when I move it to the right, the image in the lens moves to the right. This is with motion, or a minus lens.
Moving on to spherical equivalent. This is a pretty straightforward one. It's only half of the cylinder power plus the total sphere. So in this particular example, your cylinder power would be a -1. Half of the -1 would be 0.50, and if you add that into your sphere power of a 3, then your spherical equivalent is now a 250. Let's talk a little bit about the real-world application for this. If your doctor has a toric contact lens that they're looking for a spherical equivalent on, they may utilize this process. Let's say, for instance, he has a prescription of a -2, -1 at 80. If we want to know the spherical equivalent of this, we're going to take half of the -1, which would be a 0.50, and then we're going to add that in to the sphere, resulting in a -2.5 spherical equivalent. This also is very handy when you're looking at base curves. You'll want to know what your spherical equivalent is to try to identify the base curves.
Next, we're going to learn about base curve selection. Remember, the base curve is the front unground curve of the lens. Depending on the dioptrical power you're trying to make, you need to choose a different base curve because you can only ground so many curves into the back. For the purpose of this, as you learned in the last section, we compute sphere equivalent for base curve selection to use in the power in diopters. What you'll learn about this is that a 6 base will be used for a plano. That's your middle of the line base curve. And as your dioptrical power gets more minus, your curve gets flatter, including a minus base curve. And as it gets more plus, it gets steeper. Next, we're going to learn about the calculation of minimum blank size. Minimum blank size is expressed as 3 different formulas. A plus the DBL plus the ED minus the PD, the frame PD minus the patient PD plus the effective diameter, or the total decentration plus the effective diameter. All 3 of these are really the same things. But let's look at the first example here. A plus DBL. So the A measurement is across the lens, and in our particular case, that is 56 millimeters, plus the DBL, distance between lenses, which is 20, plus 64, the effective diameter. The effective diameter is twice the distance from the geometric center to the furthest edge. And then lastly, minus the patient PD, which we are told is 66. On this calculation, that would be 140 minus 66, which equals a minimum blank size of 74. What is minimum blank size, you may ask? If you look at the example over here, we have the lens, which is the lens we need to cut out in this. We move the optical center over to where it needs to be decentered to, because in this particular case, it needed to be decentered over to here to match the patient's PD. And when that happens, we then miss cutout over here because the lens is not large enough. So we need a larger lens because of the fact that it has to be decentered. Next, we're going to do the minimum blank size using the second formula, which is frame PD minus patient PD plus effective diameter. You may remember that I said earlier that these are all really equivalent because frame PD is simply from the inside of one lens to the outside of the other. So if we look all the way across here, we can look at this and see that this is 20 plus 56. So our frame PD is 76. If we take the frame PD, 76, and we minus the patient PD, which we determined was 66, it's going to equal 10. Then we go back and we add that to the effective diameter of 64, And again, we're going to get the answer of 74. Now, minimum blank size for the last formula is decentration plus effective diameter. Remember, as I said, all of these are interrelated. Effectively, the frame PD minus the patient PD, 76 minus 66, is the decentration. So in our case, 20 plus 56 equals 76, minus the patient PD is 66, gives us the decentration of 10, and then we add that to the effective diameter, 64, and again get the same answer of 74. One minor add to the minimum blank size calculation. You'll see here that I changed the PD to a monocular PD. You need to be mindful of this, because if they give you monocular PD and you're looking for the minimum blank size, it's going to be the minimum for the eye that is decentered the most. So remember, decentration here is really 2 times the decentration of the most decentered eye. So in our particular case, this would be a PD of 64 total, subtracted from 76. So 76 minus 64 equals 12 is our total decentration. And we add that to the effective diameter of 64, we now have a minimum blank size of 76 millimeters. So just be aware that if you have a monocular PD, you need to take special care to use twice the decentration of the most decentered eye. The next piece we're going to work on today is transposition. The purpose of transposition is to convert the cylinder sign of a given prescription without altering the corrective power of the lenses. It has 3 basic steps. Number 1, combine the sphere and cylinder portions of the prescription. The result will be the new sphere. Change the sign of the cylinder, but keep the same number. The result will be the new cylinder power. And then change the axis by 90 degrees. So, let's see what that looks like. If we go to our example below, you'll notice that we have a plus a quarter minus 1 at axis 40. Our first step, combine the sphere and cylinder portions. Since these have different signs, we're going to subtract the smaller number from the larger number and keep the sign of the larger number. So in our example, that will be 1 minus 0.25. That's going to equal 0.75. And we're going to keep the sign of the larger one. So that's going to be a minus. Next, we will change the sign of the cylinder. So from a minus 1, it will go to a plus 1. And lastly, we have to change the axis by 90 degrees. You'll notice here that it says add 90 to any axis from 1 to 90. So in our particular case, that is going to be 40 plus 90 is axis 130. So what we've learned here is that minus 75 plus 1 at axis 130 is equivalent to plus a quarter minus 1 at axis 40. Pretty simple. Let's try the other example here. On this example, we will have the same power on both our cylinder and our sphere. So combine for same signs. We simply add the numbers and retain the same side. So 0.25 plus a 0.75 is a 1.00. Pay no attention to the ambulance going by. We're going to retain the sign, which is a minus, and then we're going to change the sign of the cylinder, so it's going to be to a plus 75. And then lastly, the axis, before I covered over it, was 175. So we're going to subtract 90 degrees from any axis, 91 to 180. So that axis will be 85. So again, the prescription that we have there of minus 1 plus 75 at 85 is absolutely the equivalent of minus a quarter minus 75 at 175. Okay, now let's learn a little bit about focal length. Focal length is the distance it takes a lens to bring light into a point of focus. The basic formula for calculating focal length is F equals 1 over D, where F is equal to the focal length and D, the dioptric power of the lens. What you're also going to learn, because this could be asked a number of ways on the ABO exam, is that focal length and diopter have an inverse relationship, meaning that additionally, dioptric power equals 1 over the focal length. So, for example, a 1 diopter lens has a focal length of 1 meter because F equals 1 over 1. So we look at a few more of these. A dioptric power of 2 will be F equals 1 over 2, or half a meter. 4 will be F equals 1 over 4, or a quarter of a meter. 0.5 would be F over 0.5, 2 meters. 0.25 would be 1 over 0.25, or F equals 4 meters. Keep in mind that the higher the dioptric power of the lens, the shorter the focal length. The lower or weaker the dioptric power, the longer the focal length. In your review course, there are 2 questions concerning focal length. They really are the same problem, they're just worded differently, and one of them has a minor adjustment in it that you need to be prepared for. So the first question says, if a plus sphere could bring parallel rays of light to a point focus at a distance of 0.5 meters, it has what power? In our particular example, that will be D equals 1 over F. So it will be D equals 1 over 0.5, which equals D equals 2 meters. Now, later on in your practice exam, that's worded a little differently. It says, a lens whose power is half a diopter has a focal length of. So if we do that one and we do F equals 1 over D, and then we say F equals 1 over 0.5, we would get F equals 2. In our particular example, the answer that is correct and the answer you should pick, and you need to always be aware of when taking an ABO exam, is that they offer an answer of 2,000 millimeters. Well, remember, 1,000 millimeters equals 1 meter, so 2,000 millimeters equals 2 meters. Always look at the decimal and the way they relate this in the metric system. If you don't see the answer that you think should be there, keep looking, because 2,000 millimeters does equal 2 meters.
Let's talk about vertex distance. Vertex distance is simply the distance from the wearer's eye to the ocular surface of the lens. Now, some doctors are going to prescribe specific vertex distances, especially with higher prescriptions. Now, the reason for this is because the effective power of the lens changes as the distance from the eye is moved. In high prescriptions, this power change can be significant enough to cause problems. All right, let's take a look at this formula here. This formula is going to allow us to calculate the change in effective power of a lens based upon how many millimeters the lens is moved closer to or further from the eye. So this is our formula right here. We've got our diopter change, and that is equal to the millimeters moved multiplied by the power of the lens times the power of the lens divided by 1,000. So let's walk through an example here. First of all, our prescription is a -10 sphere. That was refracted at a vertex of 8 millimeters, but we now have it fitted at a vertex of 13 millimeters. So simply by doing the math of 13 minus 8, we found that our vertex change is 5 millimeters out. Okay? So looking at our math problem here, we've got 5 times the 10 diopters times 10 diopters, which will be the first part of the equation that we'll do, and that will actually result in 5 times 100 divided by 1,000. So 5 times 100 being 500, again divided by 1,000, is going to be 1/2 or 0.5 diopter change. Now keep in mind we move the lens out, so that change is going to be plus 0.50. Okay? So now the effective power is negative 9.50, and the compensated power would be negative 10.50. Let's talk about a couple of rules here that apply to this formula that we just used in this example. First, moving a plus lens out increases the power. Okay? Moving a minus lens out decreases its power. Now that's one way to think about it. We do have another way. Moving any lens out increases plus power, or moving any lens in increases minus power. As you can see in this example, the lens is moved out, so the change was a plus 50. Now, one thing that you're going to want to be careful of is the questions that you may come across on the exam on whether they're asking for the effective power or the compensated power. The effective power is how strong the lens is now that it's been moved, and it's more of a passive question. Compensated power, on the other hand, is what the lens power must be ordered to make up or compensate for the fact that the power of the lens has changed as a result of the change in vertex distance. Let's dive a little bit deeper into this with some examples.
Now we're going to do a little vertex distance exercise called weaker or stronger. So we have a +6 lens. It's refracted at 10 millimeters, but fit at 15 millimeters. If we look at the example below, this plus lens will converge the light rays to hit exactly on the retina and come to a focal point there. If we were to move that eyeball back to a distance of 15 millimeters, now that lens would be too strong. The light rays would come to focus before they made it to the retina. So that would make the lens stronger. Remember, moving a plus lens out increases its power. Okay, a little more on the example of weaker or stronger. Now remember, this is changing the effective power of the lens. So a -10 fit at a distance, a refracted distance of 8 millimeters, move to a distance of 15 millimeters. Remember, moving a minus lens out decreases its power. So this one would be weaker. +225 refracted at 12 with a fitting distance of 8. This is a plus distance, a plus lens, and we are moving it in, which moving a plus lens out increases its power. So moving a plus lens in will make it weaker also. And lastly, -375 refracted distance of 8 millimeters to a fit distance of 6 millimeters. Again, if we move a minus lens out, it decreases its power. We are moving this one in by 2 millimeters, so it is going to increase its power. So weaker, weaker, stronger. Okay, let's do a vertex distance change as it would come up on the ABO exam. In the example attached, it says an RX is +10, +2 at axis 90. The refracted vertex distance is 15 millimeters, but it is fit at 10 millimeters. The RX to be ordered is, so that is the compensated, not the effective power, but the RX to be ordered. So let's do the math real quick. Dioptrical change equals millimeters moved, which we know is 5. We went from a 15 to a 10. And then it is the power times the power, so that's 10 times a 10 divided by 1,000. So in this case, we know that that is going to be 100, so it's going to be 500 divided by 1,000, which equals 0.5. So the diopter change is 0.5. Now, what we have to ask ourselves is, how did this plus lens change? It was refracted at 15, but we moved it to 10. And we know that when we move a plus lens in, it's going to make it weaker. So effective power on this one is going to be a +950. But we're asking what is to be ordered. So in ordered, we need compensated. So we know that our compensated power is going to have to be a +10.50. Quick thing about taking the ABO exam or any multiple choice exam. If you look at this, knowing that we are going to need a stronger lens, there's really only two options. +10 is not stronger, +975 is not stronger. So that gets us down to either C or D. The one thing that we know, vertex distance has nothing to do with spherical equivalent, with elimination of this cylinder, or any of that. So this answer is gone. So the only correct answer really is D, +1050 +225 at 90.